left off with this slide on that last set, so we'll move on from there. And what I've got here are two maps with what we call isotherms, and they are like topographic lines if you're familiar with topography maps or topographic maps. I've got a winter map. Here's winter, and then I've got a summer map for North America. An isotherm works like a topographic line, and along each one of these lines the temperature is the same. So let's use this line here that I have got indicated with this little star. If I follow this star around, and right here we're at the Grand Canyon, I'm going to follow this line back. The temperature is the same along this line all the way through. And so here we are in northern Arizona, southern Utah, and the temperature as we go north is the same as it is in the Central Coast, just at the edge of the panhandle of Alaska, so the Central Coast of British Columbia and then Alaska. Right here, right at the continental edge, is the same temperature. We come around, same temperature as we head up, and we find that it's 0 degrees Celsius, 32 degrees Fahrenheit. So Alaska in the wintertime on the coast is the same temperature as this northern desert landscape in Arizona. This is what the difference between a continental landscape and a maritime landscape does. This maritime landscape allows Alaska to be as cold or as warm, if you prefer, as Arizona is in the wintertime. We can do this with all of these maps. So we find that here at minus 24 degrees Celsius, which is going to be about like 18 degrees Fahrenheit or so pretty darn cold, is the same as mid-Manitoba. Or if we follow, I think this is the right line, that's going to give me minus 12. Yeah, so minus 12, which is going to be about 25 or so, is the same as if we come around somewhere around here in Ohio, right? So here we are in Ohio. We're about the same temperature as parts of Alaska are. So stuff to consider here. We know that this is winter if without having these temperatures on the side, because the isotherms on the land masses are bending towards the equator. That means that the oceans are warmer and the land mass is cooler. In the summer, the opposite is true. The isotherms are bending away from the equator or bending towards the poles, and the water bodies are cooler because they're taking up heat. They're not radiating heat. This is giving up heat. This has got no heat to give up. This is giving up heat. All right, so this is what's happening here. So here at 40 degrees latitude, we have a temperature of 18 degrees Celsius. We're going to come in at about Los Angeles, a little north of San Francisco, Los Angeles. 18 degrees Celsius is about 68 degrees Fahrenheit. We come across the Sierra Nevadas and the Rocky Mountains, which is a hot mess. All these isolines are all over, but we follow them along and we find that we get to Winnipeg, Manitoba, or a little higher actually than Winnipeg, Manitoba, further north. And the temperature here in the summer is the same as Los Angeles in the summer. So stuff to consider, and that's because this landmass is giving off so much heat, and this water body is taking up that heat, taking in that heat energy so it can re-radiate it at a later date. We can take this from this continental landscape and model and consider a global model. Here's January. The sun is in the southern hemisphere in January. let's see, 23.5 degrees. So it's sitting somewhere right in here. We're not quite at 23.5 because that would have been December down here. So we're right in here, close to 20. And the equator, the thermal equator, the hottest part of the planet along these gradients is occurring right here in the ocean, further north. The landmass is radiating a lot of heat, so it's really warm down here. We get into an ocean environment which is radiating heat, so it's a little warmer. Africa, we're coming through the Congo. Indian Ocean is pulling this down towards Australia and then back into the Pacific. Just some really important places to note. Here's Siberia, really, really cold, right? And here is Greenland, really cold, right? So we've got enough water and mobility through here to keep this warmer than right here. All right, take a mental map of this, although that you can use the slides to go back and forth at your own leisure later on. Mental map of this as we turn and look at the July scenario. And just for reference, that thermal equator was down here in January. It's way up here in East Texas in July. In January, the thermal equator sat down here. Now it's up here, and it didn't travel nearly as far because this is a large landmass. In fact, it's part of this landmass as well. So we've got this large landmass that's really hot. At this same latitude, we don't have a lot of land. So the land that's influential is really the continent here that's driving and pulling this thermal equator up here. We stay at a pretty high elevation for the most part through here, and then we dip back down into the Pacific Ocean. So this is the amount of influence land masses and ocean masses have in terms of where the water and the land is warmest and coolest over the course of a year. All right, guys, as always, if something is not grooving, give me a shout, send me an email. We can set up a meeting. We can have a chat on campus if we ever get to campus. I don't know if we're back yet. I'm recording this before the start of the semester, so hopefully we're there. If not, definitely we can talk in a number of different ways to make sure that you are doing well in class and understanding these concepts. Talk to you soon. Bye.